Welcome back to Optical Communication video lecture series. In this presentation, we are going to discuss about introduction to fiber waveguides and ray transmission. What are waveguides? Waveguides are the structures which are going to guide a wave from one end to other end. Here, in this case, one end will be your transmitter and the other end will be your receiver. Okay. So, in a fiber waveguide, what do you mean by fiber waveguide? Optical fiber cables are known as fiber wavelengths, and optical fiber cables are used to transmit light rays. Hence, we are going to discuss about fiber waveguides and ray transmission theory in this presentation. Okay. Next, by the end of the session, you will be able to understand about electromagnetic spectrum. That is, what is electromagnetic spectrum and what are the different wavelengths and frequencies where we are going to find different ranges of lights like optical wavelength, what is optical wavelength, what is radio wavelength, what is micro wavelength, and we are going to see that. Okay, we are going to learn about reflection, refraction, and Snell's law in this video. Okay, coming to electromagnetic spectrum, the radio waves and light are electromagnetic waves. What are the two electromagnetic waves categories? Radio waves and light are going to come under electromagnetic wave category. Here, the rate at which they alternate in polarity is called their frequency, measured in hertz. Okay. When a ray is transmitting, it is in alternating in nature. Okay. So the rate at which it is going to alternate is considered as frequency. Coming to the speed of the electromagnetic wave in free space is approximately 3 into 10 power 8 meter per second, where the distance traveled during each cycle, that is from one normal peak to alternate peak, that is considered as one cycle or a complete cycle, and the distance traveled is read as wavelength. Okay. In fiber optics, it is more convenient to use the wavelength of speed or wavelength of light instead of the frequency with light frequencies. That is, in fiber optics, we are going to deal with wavelengths instead of frequencies. Okay. So, since we are going to deal with wavelengths, we need to know the units. The units used for wavelength in fiber optics is microns or micrometers, and they are given as 1 micron is equal to 1 into 10 power minus 6 meters, and 1 nanometer is equal to 10 into 10 power minus 9 meters. Okay. Fiber optic uses visible light and infrared light. Okay, in fiber optics, we are going to transmit one visible light or infrared light. Okay, infrared light covers a fairly wide range of wavelengths and is generally used for all the fiber optic communications. Okay, infrared light is generally used for all the fiber optic communications. Okay, visible light is normally used for very short range transmission using a plastic fiber. So, visible light is transmitted using a plastic fiber. When we are using fiber optic cable, that is made up of glass, we are going to transmit infrared light, not a visible light. Okay. Electromagnetic spectrum and wavelength. Here you can observe that what are the different waves we can observe. One is gamma wave, gamma rays. Gamma rays range from 0.001 nanometer to 0.01 nanometer. X-rays range from 0.01 nanometer to 10 nanometers. Coming to ultraviolet rays range from 10 nanometers to 1000 nanometers. And infrared rays are going to lie in this range, 1000 nanometers to 0.05 centimeters. Okay. From that, you are going to find your radio waves. In radio waves, you are going to find radar, TV, FM, and amplitude modulation waveforms. Okay. These are the functions we are going to do in radio waves. Okay. Coming to light, visible light is going to lie in between this range, and the range is given as 400 nanometers to 800 nanometers. Okay. Now let us separate that visible light spectrum, and here you can observe that in visible light, from this side you are going to see higher frequency and this will be your lower frequency. That means your wavelength will be high on this side and wavelength will be low on this side. So your red color light is going to have higher wavelength and lower frequency. Violet color is going to have higher frequency and lower wavelengths. And these are the different lights that we can observe in visible light spectrum. We also call this as VGR. Okay, violet, indigo, blue, and green, yellow, orange, and red. Okay. Coming to the next topic we have is reflection. The law of reflection states that when a light ray is incident upon a reflective surface at some incident angle, say phi 1, from imaginary perpendicular normal, the ray will be reflected from the surface at some angle, say phi 2, from normal, which is equal to the angle of incidence. Okay, that means let us see that if this is normal, this is the normal to this surface, and this is imaginary. Okay, we are not going to say this, we are going to imagine this. If a light ray is incident on this surface, now it is going to make an angle, and this angle is known as angle of incidence, and is indicated by phi 1. Now the ray is going to get reflected. Okay, this angle is known as phi 2, and this angle is known as reflected ray. Okay, and the angle is, this ray is known as reflected ray, and the angle is known as angle of refraction. In this case, both angle of incidence and angle of refraction will be same, and the law is known as law of reflection. Coming to refraction, since we have seen reflection, we are going to see refraction. Coming back to reflection, you can observe that the reflected ray, this one, and the incident ray, this one, both are in the same plane. But in case of refracted, you are going to see that the plane is changed. First, let us see what is refraction. Refraction occurs when light ray passes from one medium to another medium. That is, the light ray changes its direction at the interface. Refraction occurs when density of the medium changes. That means if we are traveling from one medium to another medium, along with the medium, the densities are going to change. Hence, we are going to experience refraction. Refraction occurs at air and water interface. That is, when light is traveling from air to water, it's going to experience refraction. The straw in a glass of water will appear as if it is bent. That effect is due to refraction. The refraction can also be observed at air glass interface. If the light is traveling from air to glass, we can also experience refraction. Okay. This is the process in which we can. This is the image for refraction. Here you can observe that incident ray is falling in this direction, and then what we expect is to travel in a straight direction, but we can observe that it is bent in this medium. Okay, when coming from one medium to another medium, it is bent. Okay, here the medium is lesser denser medium. Okay, here the medium is more dense medium. So for lesser denser medium, we are considering air, and for more dense medium, we are considering glass. Okay, if it is traveling from lesser denser medium to higher denser medium, the ray is going to bend towards the normal. If it is transferring from more denser medium to lesser denser medium, it is going to bend towards the plane of the surface. Okay, away from the normal. Okay, now here we are projecting reflected ray and refracted ray. Okay, here if the light is traveling, this is your refracted ray, because here we are transmitting ray from this medium, hence this will be your refracted ray, and it is bent from normal, away from the normal, and here you can observe that it is bent towards the same medium. That means this medium is one medium and this is your second medium. So in case of refraction, you are going to see that your light ray is being transmitted from medium 1 to medium 2. In case of reflection, you are going to observe that your ray will be transmitted in the same medium. Okay, now using this property, we are going to check how the light transmission is being obtained, and it is known as total internal reflection. Okay, now we generally know that there are two theories for light. One is your wave theory, where we can observe that light rays are going to transmit in the form of vibrations. That means this particle is going to vibrate this one, and in the same process light ray is going to transfer, and this is known as, here you can see the point source, and then here we are observing spherical wavefronts. Okay, this is due to vibration wave theory, and this one is ray theory. In this you can say that rays are transmitting directly. Okay, this is your ray theory, and here we are going to learn about ray theory. We are going to use ray theory in our optical fiber communication. Okay, refractive index. What do you mean by refractive index? The amount of refraction or bending that occurs at the interface of two materials of different densities is usually expressed as refractive index of two materials. That means, going to the previous figure, here the amount of bending that has occurred. Here you can observe that we are expecting a light to travel in this direction, but this is the bend. Okay, so if we are expecting a light to travel in this direction, then from this point to this point you are going to observe the bend, and it is indicated as refraction. Okay. Refractive index is also known as index of refraction and is denoted by n. Refractive index is denoted by n. Based on the material density, the refractive index is expressed as the ratio of velocity of light in free space to velocity of light of the dielectric medium. That means here we can observe that there are two mediums. One is free space and the other one is dielectric. So here the refractive index is expressed as the ratio of light in free space to ratio of light in dielectric medium. Okay. Here you can observe the formula. The refractive index for vacuum and air is given as 1.0 because here we are going to divide it with the same value. So we are going to get 1. For water, the refractive index is 1.3 and for glass, the refractive index is 1.5. Here you can observe the formula. It is the ratio of speed of light in air to speed of light in any given medium. Okay. Snell's law. Coming to Snell's law, Snell's law states that how light ray reacts when it meets the interface of two media having different indexes of refraction. Snell's law gives the reaction that light is going to show us when it is going to travel from one media to another media. It is known as interface. Okay. Let the two media have refractive indices N1 and N2. Let N1 be the refractive index of first media and N2 be the refractive index of second media, where N1 is greater than N2. And then we are going to see phi1 and phi2 are the angles where the angle of incidence and angle of refraction is measured. Okay. Then according to Snell's law, the relationship exists between the refractive index of both the materials given by the relationship between both the materials is given as N1 sine phi1 is equal to N2 sine phi2. A refractive index model for Snell's law is shown in the figure. Here you can observe the figure. Okay. In this figure, you can observe that here the incident ray is projected in this direction, and then you can observe that what we expect is the ray to travel in this direction, but instead of traveling straight, it is going to experience some bend. Okay. Here, using this figure, we are going to explain some theory over here. Okay. A refractive index model for Snell's law is shown in the figure that we have observed right now. The refracted ray will bend towards the normal. Here you can observe that this ray is bent towards the normal. Okay. When N1 is greater than N2 and will bend away from the normal when N1 is greater than N2. If N1 is greater than N2, then it is going to bend in this direction, not in this direction. Okay. That is what you need to remember. Okay. The equation can be written as N1 by N2 is equal to sine phi2 by sine phi1. That is, here we are writing Snell's law. Okay. Now, you can observe that this is the image that we are discussing, and this is a medium 1 and this is medium 2. Okay. Here in this region, you are going to experience your light ray if N1 is greater than N2. If N1 is less than N2, it will be in this region. Okay. Now, from the previous equation, we can write that this equation shows that the ratio of refractive index of two medias is inversely proportional to refractive and incident angles. That is, ratio is inversely proportional to the refractive index and the angle of incidence. And the refractive index is given as N1 is equal to C by V1, N2 for N2 it is given as C by V2. Okay. Speed of light to speed of light in free space. C is the speed of light in free space, where V1 is the speed of light in that particular dielectric medium. Here, using previous law, in this law we are going to substitute values of N1 and N2, and we are going to get this one. C and C will be eliminated, and then we are going to have V2 by V1 is equal to sine phi2 by sine phi1. Okay. Now, in this video, what are the terms that we have seen? One is UV rays. UV means ultraviolet rays. The other one is infrared rays, we have discussed. Okay. And then the other one is refractive index. Reflection, what do you mean by reflection? The change in the direction of light when it is interfacing a new media, it is going to change into the same media. That means a forward going light is going to get reflected in that same direction. Refraction is also changing the direction of light, but it will be in the second medium. Okay. In case of reflection, media will be constant. In case of reflection, the medium is going to change. Okay. In the next video, we are going to learn about critical angle, total internal reflection, and some problems we are going to solve on that. Okay.